I'm happy to introduce our next speaker, Simon Sandberg from Carlsbad University. So Simon is doing his PhD research. He's a PhD student at Carlsbad University. He's doing his PhD research with Red Hat for over 2 years now. And I guess he will tell us all the details. So good to have you here.
Yes, thank you for having me. Yes, so I've already been introduced, but I'm not working entirely alone. I also have my main supervisor, Anna Brunström, at Karlstad University, and have had a lot of help from three really nice Red Hat engineers by the name of Simone, Tuke, and Jesper. And these last two, Tuke and Jesper, they are also involved into other research collaborations with Karlstad University regarding eBPF. So what I have been working on with these people is to develop a method to continuously and efficiently monitor network latency by using the emerging eBPF framework in the Linux kernel. So that is what I'm going to present here today, and I'm going to start with talking a little bit about why it's important to monitor network latency in the first place, and go through some of the problems with existing tools for monitoring network latency. I will then go on to present what this eBPF thing is, because I guess not all of you are that familiar with it, and talk about how we used it to solve some of these problems. And finally, I'm going to present some results from my work and also some plans for how we plan to improve my work in the future. So, why should you monitor network latency? Well, the short version of it is that for any type of interactive application, the latency is very important for, well, the interactive part. And if your application runs over the network, then network latency has been shown to have a huge impact on the perceived quality of experience. So in research, there's right now a lot of focus going on with the tactile internet, where you need latency that is consistently in the range of like maybe 1 to 10 milliseconds for the applications to even work. But you don't have to go that extreme. Even for many of today's applications, latency is very important. Take, for example, video conferencing, which I'm sure a lot of you have had to do a bit more than you maybe wanted during these times of pandemic. And there, the latency can be the difference between basically having a stuttering mess where everyone is talking over each other and everything is flowing along nicely and it basically being like being in the same room. But even for applications you maybe not even think of as that interactive, like normal web browsing and web shopping and web searching, latency has been shown to play a huge role. Already back in 2006, Amazon found that for every 100 milliseconds of added latency, they lost 1% of their revenue. And Google found that delaying the search results by half a second decreased their traffic with 20%. So latency really matters. People do not like waiting, and people haven't gotten more patient today than they were back then. So if you're some type of service provider and you care about your users' quality of experience, you also need to monitor your network latency. Of course, network latency monitoring can also be used for other things related to just general network management, such as validating service level agreements, detecting and troubleshooting network issues, and even detecting certain types of network attacks. So when you want to monitor latency, one of the perhaps most common tools to do it is the traditional ping tool, which I'm sure most of you have used at some point. This is a very simple utility. It just sends out an ICMP package and measures the time until it gets a response. Now, this is a form of what's known as active network monitoring, because you're actively injecting a network probe on the network, and you're monitoring this probe that you injected. So there are many other tools that can also monitor network latency that are based on this concept of active monitoring. There's a bunch of different ping versions, fping, hping, nping, and so on. There's IRTT, net latency, RIPE atlas, mesh ping, and many others. And while these, of course, work slightly differently, they use different protocols and so on, they still use this fundamental principle of injecting traffic and monitoring these probes that they inject. And there's nothing inherently wrong with this. This is a great way if you want to get the idle latency of the network in a very controlled manner. But the problem is what you typically want to know is the network latency that that your application traffic experiences. Because this is, in the end, what the end users will notice, is the latency of the application traffic. And in this scenario, ping has a few drawbacks, or active network monitoring in general has a few drawbacks. One is that, of course, it adds overhead on the actual network. You're injecting additional traffic. And if you want more granular measurements and you want to monitor a lot of different targets, then this can actually add up to quite a lot of probes. And this additional network traffic may also interfere with your actual application traffic. But what is perhaps the most important problem here is that this active network monitoring doesn't actually tell you the network latency that is experienced by the application traffic. It only tells you the network latency that the probes experience. And now on the networks we have today, there are many devices that this traffic will pass through that may treat the probes from these network monitoring tools and the actual application traffic very differently. For example, you might have load balancing, which sends the probes down a completely different path than the application traffic. Or they might make use of active queue management, where the sparse probes will typically get to bypass the queues, whereas bulk application flows will sit around in big fat queues waiting for a long while. So trying to monitor application network latency with active network monitoring is a little bit like trying to find out how long cars are stuck in a traffic jam by sending out a guy on a scooter and measuring the time it takes for this guy to get through the traffic. In some places, maybe the scooter has to actually sit around in the same queues as the cars, and then you might actually get some relevant latency data. But in many places, this scooter guy is just going to zigzag between all the cars, or maybe take an entirely different route altogether. And the time that you get from this scooter guy is not really going to tell you much about how long your cars are stuck in the traffic jam. So if we can't really use active network monitoring for this, what can we do instead? Well, we can make use of something that is known as passive network monitoring instead. And with passive network monitoring, you're not generating any additional network probes that you send out on the network. Instead, you're simply observing the traffic that is already there. So when you want to use passive network monitoring to discover the network latency, you typically try to match outgoing packets with replies to those packets to calculate the round-trip time between the time between when you saw the original packet and the time you saw the reply to this packet. There are much fewer tools that can do this. One of those tools is called passive ping, or ePPing. This tool was developed by Kathleen Nichols back in 2018, I think. It's a very cool tool. It can tell you, it can continuously monitor the round-trip times for TCP traffic throughout the lifetime of the streams, and it can do it on live traffic, not just on packet captures. And what this ePPing uses to do this is a feature known as TCP timestamps. When TCP timestamps are enabled, every packet will contain two additional fields called tsval and tsecr. So to explain a little bit how this works, let's just take a little look at the example here. So when TCP timestamps are enabled and A here wants to send a packet to B, it will put its own timestamp in the TSVAL field, and it will send it off to B. When the packet gets to B, well, B has to ACK the packet. A knows that B received the packet. So it sends the ACK. And when it does this, it also in turn puts its own timestamp in the TSVAL field. But importantly, it also echoes the timestamp it saw from A in the TSECR field. So when the packet gets back to A, then it can see what time it sent out the original packet. Now, even if we don't really know the original clocks here, we can still use this to match packets and replies. So that the way passive ping works here is basically that we have some capture point. It could be one of the end hosts, A or B, or it could be any point in between that is able to see the packets going in both directions. So, for example, a firewall or a router. And when this packet then that A sent gets to the capture point will see that this packet contained a TSVAL. So it saves the time when it saw this packet using this TSVAL combined with the flow tuple to create an identifier for this packet. And when B ACKs the packet and the capture point later sees this packet at time T4 here, it can then look up, it will then see that the packet contains a TSECR. So then it will look up its saved timestamps to see if we've seen a packet matching this TSVAL previously. And in this case, yes, we saw a packet going in the reverse direction, A to B, back at T1. So we can calculate the RTT by simply subtracting T1 from our current time T4. Now, note that this only gets us a partial round-trip time. So it gets us the leg between the capture point and the receiver B in this case, which is not necessarily the full round-trip time that A sees. But whenever B sends some data to A, then we can run the same process in the other direction. So then we get the other leg. And by combining these two legs of the RTT, we can get an estimate of the full RTT, as well as the individual components on either side of the capture point. And if we then deploy multiple capture points, we can, of course, calculate multiple components of the RTT between all of the capture points. So what's the problem with this passive ping that already exists, and why not just use that? Well, the problem with it is that passive ping, just like most tools for passively monitoring network latency, relies on packet capturing. And packet capturing, unfortunately, has quite a lot of overhead. And when you try to run it at link rates of 10 gigabits, 40 gigabits, or even 100 gigabits, they typically can't keep up. And they will start missing a lot of packets. We saw this clearly with passive ping or ePPing. In one of our experiments here, the blue line shows the number of packets that passes through our device, whereas the bottom orange line there shows the number of packets that passive ping saw, which is significantly less. As the green line shows, passive ping only saw between 20 and 5% of the packets in this case. So passive ping is actually missing most of the packets. And this has a couple of consequences. By missing a lot of packets, we're of course missing a lot of potentially useful round-trip time samples. But because of how TCP timestamps works, it's also important that we only ever match the first instance of a TSVAL with the first instance of a TSECR. And the only way to know that we're matching the first instance of some packet in a stream is by seeing every packet. So if we drop a lot of packets, we can't really know if we're matching packets correctly, and we might get incorrect RTT samples. So this is unfortunate, because passive ping is a real cool application. But due to this packet capturing, it doesn't really scale to high link rates. But what if we didn't need to capture the packets at all? what if we could just take a little peek at the packets as they're traversing through the normal Linux network stack? Well, this is exactly what BPF allows us to do. So, eBPF, what is that then? Not sure how many of you have heard about eBPF before? Quite a lot of you, good. So basically, eBPF is a runtime environment inside of the Linux kernel that allows you to attach small custom programs to various hooks. And whenever these hooks trigger, they will run your custom little program. So the way this typically works is that you compile your eBPF or your custom program into eBPF bytecode. And you can think of this a little bit like Java bytecode. It is the instruction set that the eBPF runtimes understands and can interpret. But before you can attach your custom program to one of these hooks that I will talk a bit about more later, you need to load it into the kernel. And when you do that, a part of the kernel called a verifier will statically analyze this program to make sure that it's safe, that it doesn't access any memory out of bound, or that it doesn't get stuck in any infinite loops. So this does restrict a little bit of what you can do in these custom programs, but it also ensures that your custom program can, for example, never get stuck or crash the kernel. So it's in that regard a little bit safer than, for example, kernel modules. If your program passes this verifier, it's typically just-in-time compiled into native instructions to get good performance, and after that it can be attached to one of these hooks. So what you use eBPF for depends a little bit on what hooks you use and what your custom little program does. One very common use case is observability. In addition to thousands of static trace points that you can attach programs to, you could also, for example, attach a program to every single kernel function, or virtually every kernel function at least. And this gives you a lot of insight into what the kernel is doing. You can see when different kernel functions are called, how often they're called, with what arguments they are called, and so on. And related to this is then also security. Because for security, you typically need to observe some sort of suspect behavior that you want to take some action against. And with certain hooks, you can also actually take these actions. You could, for example, block certain system calls that contain some arguments you don't like, or you can drop a packet that you think looks a bit suspicious. Finally, we also have, or well, not finally, but one other common use case is networking. And when we talk about eBPF and networking, two hooks you will hear a lot about are express data path and traffic control. Now, I don't really have time to go into details about what these hooks do exactly, but in general, these hooks basically trigger whenever a program is sent or received. And they allow your little custom program to access this packet, so you can see the entire packet. And it can also write data to this packet. So you can rewrite some header, or you can add a header or remove a header. And you can also take some actions on these packets, like, for example, dropping the packets or redirecting them to a different interface. So basically, you get a programmable data plane inside of the Linux kernel, which is really cool. You can use this to implement a lot of different things. People have, for example, implemented very efficient load balancers and firewalls with this. But for my case, all I really need is to be able to inspect these packets without having to first capture them and copy them up to user space. So let me present evolved passive ping, or ePPing, where we've pretty much taken this logic I presented earlier with matching packets and replies and implemented it in eBPF programs that run whenever a packet is sent or received. So this eBPF program will then parse the packet. If it sees a tsval, we will save the time we saw this packet in a hash map. If we see a valid tsecr, we will look up our hash map to see if we've seen a packet going the opposite direction with the matching tsval previously. And if we do, then we have a match, so we can calculate an RTT by subtracting the looked up timestamp from our current time. And finally, when we have that RTT, we simply just push that RTT up to a user space component that prints it out. So, did this work? Did we get any performance improvement? Well, we used a very simple test up here to test it. We have a sender and a receiver, and in between them a little middle box that, in this case, basically just acts as a router. It just forwards the traffic between them. And then we decided to passively monitor the network latency on this middle box. So the blue bar here is the baseline of not using any monitoring at all, whereas the orange bar is for the original passive ping that uses packet capturing. And finally, the green bar is for our ePPing application that instead uses eBPF. So, for example, when just running with 10 simultaneous iPerf flows, all of these hit roughly 55 gigabits per second on this particular system. And obviously, the baseline has the lowest CPU usage, as it only forwards the packets. Running the monitoring, of course, adds some CPU overhead, but evolved passive ping here does a lot better than the original passive ping. And importantly, ePPing does this while actually running and capturing every packet, or rather seeing every packet, whereas the original passive ping misses around 94% of the packets in this case. So even though we're processing all the packets, we're still having a lot lower overhead. So I'm running out of time here, but so just briefly, we then also actually moved the bottleneck to this middle box by restraining it to using a single CPU. So now this middle box that is busy forwarding the traffic is already running at 100%, just forwarding it. And then we're adding this monitoring on top of that, and that will obviously add some additional overhead, so we will lose throughput. And I've included the original passive ping here just as a reference, but as I've noted already, it doesn't really work because it misses most of the packets. Our ePPing, on the other hand, does work, but as you can see, when we increase the number of flows here, it loses quite a lot of performance. And the reason for that is with more flows, we get more RTT samples, and simply reporting all of these RTT samples has a lot of overhead. So in the case of 1,000 flows here, we're reporting roughly 140,000 RTT samples per second, which is perhaps a bit more than you really need or even want. So we sort of just did a quick fix where we added a rate limit to the number of RTT samples per flow and second. And then we got sort of the green dashed line there, which still has some overhead, but it's now fairly constant overhead compared to the baseline. So I'll skip the summary for time concerns, but basically this is what we have done, and in the future we want to improve ePPing by improving the way we report this RTT. Instead of reporting individual samples, we want to sample and aggregate them in some meaningful way to reduce the overhead a bit and get some more meaningful output out of it. And we also want to add support for some additional protocols, because this matching packets and replies is not really limited to just TCP. We could also use it, for example, for DNS or possibly even QUIC. So that way we could get sort of a more general network latency monitoring tool. So thank you for your time and attention. And if you have any questions, I'll do my best to answer them.
Let's send the speaker. So yeah, thank you, Simon. We've got a couple of great questions again. So is it possible to monitor UDP traffic?
Raw UDP traffic, unfortunately, no, because there's nothing that guarantees that you even get a reply for a raw UDP packet. So UDP traffic on its own, we can't really passively monitor in this way. But what we can do is potentially monitor some type of applications that run on top of UDP. For example, DNS that runs on top of UDP, you will typically have an identifier that you can then use to match DNS queries and DNS replies and get the RTT for those specific applications. But general UDP traffic, unfortunately not.
All right, now to the next question. What about encrypted network traffic? Does the encrypted header itself contains enough information?
Yeah, so if it's encrypted TCP traffic, that's fine, because we're just working with the header, and that contains all the information we need. The challenging part can be that we're also moving towards more encrypted protocols in general, like QUIC, where most of the header is also encrypted. But for QUIC specifically, they have also suggested using a spin bit just to actually expose information about the run trip times. So for QUIC, we could use that. But if the entire header would be encrypted, then we're screwed.
All right, and can the proposed method be used for measuring latency beneath 1 millisecond? Or the limit is higher?
Sorry, can you repeat the question?
So under 1 millisecond latency, can it be used to measure latency beyond
yes.
1 millisecond?
So TCP timestamps themselves typically only update every millisecond. But because we're making sure that we only match the first instance of a TCP timestamp and the reply to it, we can actually measure RTTs below 1 millisecond.
All right. Is anyone using ePPing already?
Right now, not as far as I'm aware, no. So we're sort of trying to scout around a little bit. We have some interest from some people, some ISPs that want to monitor their customers' network latency. So we will be grateful for any type of feedback on how we can, for example, aggregate these RTTs in a meaningful way for their use case. So if you have any use cases yourself for this, then please come speak to me and we can think about how to use this in a good way.
Great. And what BPF hook are you using to collect the data?
Yeah, so I've used 2 eBPF hooks in my case. It's Express Data Path, XDP, and Traffic Control, TC. Because XDP only works on ingress traffic, so I use Traffic Control for egress traffic.
Okay, great. And the last question, are there any other tools doing passive monitoring besides ePPing? And how would you approach compared to them?
Yeah, so there are a few, but they're very limited. So one you can use is just Wireshark itself, or the terminal version T-Shark. But this will eat up memory, and it also uses packet capturing, so it has similar limitations as normal passive ping. Plus, eventually, it will run out of memory because it keeps saving all the packets it has seen in memory. And I've also seen one tool from Ericsson Research that I'm looking a bit more into right now. That is, forgot what it was called, but I can look it up if you're interested. But this tool also uses packet capturing, so still has the same limitations.
All right, so let's thank our speaker again. Thank you, Simon. And now we go into another break. Now, you might have noticed that, oh, yeah, I see the barista is here. So I was told that he's going to escape downstairs. So we have the cafe downstairs. Just take the stairs on your right as you exit the room. And there are going to be coffee tasting there. So please be welcome to attend. Thank you.